Thank you all, the audience in the room and also the online. I'm really honored to be a speaker today. This is my first visit to ANT. It's a very nice campus and the resources you have are awesome. So I learned a lot from your students' talk today. Now, today I will talk about the cyber physical social systems. So that's the foundation of our work. And we'll talk about the next frontier. So what we can do, what we are doing now with cyber physical systems, what's next. So everything today are made of cyber physical social systems, right? So now, so I'm, as I said, I'm Associate Director of the CR2C2, my most important designation. Slide, please. It was doing it. Okay, okay. It's, Caesar, some technical problem. I think some server was, I think, attacked. I think this was the denial of service attack, right? This kind of attack can happen. Denial of service. So what happens? The attacker with just one computer, it can use your regular people's computer, non-attacker's computer, and it can create a distributed denial of service attack, right? And then any server, it's like a Netflix server or any Amazon server, they can make it unworkable so that when you try to watch movies, you see that there is no service because there was a distributed denial of service. But you see how one attacker can create this box and makes your system unavailable, the service unavailable, the legitimate users will suffer from it, right? So this is very easy to do, just like that, what happened. So thank you, Caesar, for helping me. So what is cyber physical social systems? So you have the physical systems, right? So it's a roads, it's a spacecraft, it is your ports, airports, everything is a part of cyber physical system. And you have a cyber system, either it's a space shuttle or it's your cars or is a road or the ports, airports. Those are controlled by a cyber system. And then you have a social system. So this is the Clemson football game. It's a very big event. So, and also the people in our society, right? So they're interacting with your cyber physical system. So they're using the physical system. So they're all interconnected, right? So it's creating a network. So how they're connected? Communication. It's a wired communication and also wireless communication, depending on what functions it is performing. So it's very important. So social system very important for the context of CR2C2. So we have to get input from the society, from people, and also we have to give the service to the people, right? And everyone in our society. So that's very important to bring in the social system. So the way we achieve it, when we deploy a system, we talk to the users, we do survey, we interview them, and also we get just input from them, like how much they're using a particular system. And also we try to improve based on the input. So social system is an integral part of cyber physical social system. And they're communicating in a seamless fashion. So the keyword is seamless, and we'll see that why seamless is so important. So what we can do in terms of communication research. So I will now briefly talk about some of our research projects. So the projects I'll present are the outcome of a very hard work of my graduate students, some of my current graduate students and some of my former graduate students. So they are brilliant. They are very dedicated, and because of their hard work, we were able to achieve the results we were able to achieve. We developed several products, software products, because of our students at Clemson University. So thank you, my graduate students. I know some of you are listening today. So first project I will discuss is a cloud-based speed advisory at signalized intersections. So we thought that for DOTs, public agencies, rather than buying computers and again going through changing the computers every year, every few years, why can't we use the cloud services provided by commercial cloud providers? Some DOTs are actually doing it, but there is some security concerns about using the public cloud. So we did some research actually that how cloud can be a commercial cloud, what we can do as a user. So our work with the cloud would be secure and private. So that's will not present that research, but I presented that in the last talk at the university. So we have these different services in the cloud services, right? We are using the serverless architecture in Amazon Cloud. There's a server-based and serverless. So it's less work for you if you are doing a server-less architecture. So we are using these different DynamoDB, which is a database, and Kinesis is just as a data streaming service in the Amazon Cloud. So what we are doing, so initially we started with real vehicles, connected vehicles, communicating with the Amazon server. So we were looking at the latency to send the data, and once the data is processed, get the data back. So we did with 5 or 6 vehicles. We were, and so the latency was okay for application for speed advisory. But then we thought that 5 vehicles are not representative of the real network, right? So we want to use more vehicles, 50 vehicles, 100 vehicles that are communicating with the cloud. So it's providing data, basic safety messages. So the location, the speed, and so accelerations, all those data provided to the cloud. And also the traffic signals, it's a corridor, right? So each traffic signal is sending data through Kinesis, and also we are sending basic safety message, the trajectory data to our cloud, Amazon Cloud that we were using. So and then with the serverless architecture, we are processing the data, and I would show that how the mathematical framework is determining what should be the speed of the vehicle approaching the intersection, so they will have minimum delay. So, and we developed an algorithm which is determining that, and we are providing that data. This is our interface, and then we are providing that data to each connected vehicle, so that if you drive at this speed, then you will have minimum delay. So the speed advisory is going back to the connected vehicle. But so when we are doing a lot of vehicles, we actually use the simulation, Sumo, and it interfaces in real time with the Amazon Cloud. So that's a nice development that we did. So in real time, it was communicating with the Amazon Cloud with this interface. So we had 3 major algorithms. One is the platoon assigner. So it is based on the data from connected vehicles. Now we are considering all vehicles are connected in the corridor. So it is we are assigning platoons. So how many platoons will make the most efficient movements of through the intersections? And then we have other 2 optimizer. It is associated with the leader of the CV platoon. So we are minimizing delay for the leader vehicle in each platoon, right? We have 3 platoon. So for each platoon, we are minimizing delay. And the last algorithm is minimizes inter-vehicle gaps of the follower vehicles. So we were running 3 this optimization, and there are like mathematical equations. So we have a paper published. So if you want to look at the equations, it is the development of the equations. You can look the sources. Each slide I will present, where it is published, so you can look at the actual algorithms. So once we do that, and then we provide the information to connected vehicles. As you can see, when we did not have any advisory, and then the green is when we had the advisory. So the stop delay at intersections reduced significantly with speed advisory. So now you may say, what about the processing time? Because you are sending data in real life. You are when you're on the road, you send to the Amazon Cloud, right? And we were sending it to LTE. So the latency upload from vehicle to AWS, application processing time. So our algorithms are running, and the download, now you have to download from the Amazon server to each vehicle. So the latency is okay, it's in milliseconds. So for low traffic volume, you can see our latency, and for the high traffic volume, but it did not change much, the latency. when we were going from low traffic density to high traffic density. So one of the major thrust of our research group is quantum computing. We'll talk about the quantum computing lab we have. We work a lot on quantum artificial intelligence. So here we designed a virtual traffic light. Now we talked about how to improve the traffic operation, right, when we have the signals. But now we are saying that take out the traffic lights because it's a lot of cost to putting the lights, the signal controllers. Just have virtual traffic lights. And then each vehicle will have an in-vehicle display. So it will, when they're an intersection approach, they will know that whether they should go green or they should stop, red and yellow. So they will alert them to stop. So this is the in-vehicle display. And we are getting data. So it's running through a roadside device. So all vehicles are sending data to a roadside device. And we'll have a CV2X device or DSRC device. They will have a very low delay. And then the roadside device will send the data to a quantum computer. So we are using D-Wave quantum machines. So they're pretty good in optimizing. So they're optimizing so that we run an algorithm. They have all the vehicles in the approaches will have minimum time, minimum delay, and we'll also give priority, like which vehicle should go first, which should go second. So we do in a very systematic fashion. We have shown that it works in the real world testing. And also we have done simulation for many vehicles too. So what is the reason for using quantum computers? They're pretty good in optimization. So it is proven. Now, quantum is under development, but they do a very good job in optimization. So because you can see that the classical computer energy equation, they have to go through this energy curve. But quantum, because of the quantum tunneling, which is the function of quantum physics, it can tunnel. So it can go from this to directly to this. So it can reach, you see the local, so the classical optimization, is going to probably same time to the local minima. But if you want to go to the global minima, it has to go through the energy curve. But quantum, it can just tunnel. So it can quickly go through from here to here. So it can reach the global minima much faster. And sometimes you see that what happens with classical computer, if you have a very large intersection, lot of data, it just sometimes cannot go to global minima. Its problem is too complex. But for quantum, it's very easy. And we saw that it's working very well with quantum optimization. So we saw that in terms of processing, it is reasonable to send it to D-Wave and get it back. Now, this is a project that is actually implemented in Clemson in a real intersection. So we were generating just with a simple low-cost video. So this is the setup. So we are using CV2X radios, so which can transmit data very quickly. So the delay is within 100 milliseconds. It's not sometimes very quick. And DSRC also both runs on 5.9 gigahertz, so the delay is very less. And we have the pedestrian safety message and basic safety message, right? So it's according to the SAE standard. So you have to develop the timestamp, latitude, longitude, altitude, position, accuracy, speed, heading, acceleration. But now if you have this radio, this CV2X or DSRC radios, it will generate this data, right? But we thought that if you're using for pedestrian, they will not carry CV2X devices, right? Or they will not have the, you may not have BSM devices, the radios in each vehicle. So we thought, how about we use video analytics to generate this, the basic safety messages, pedestrian safety messages. And that's what we did. We used algorithm to develop the basic safety messages and pedestrian safety messages. And we applied it for pedestrian collision warning. So at an intersection in Clemson, we'll show the intersection a little bit later. So we are looking at the intersection. We are looking at the pedestrians. We are looking at the vehicles. And we are running an algorithm to determine, based on the position, speed, heading of the pedestrians and vehicles, whether there is an imminent crash. When we see an imminent crash, we inform the drivers and we inform the pedestrians. And so these are in the intersection. But we have another project from the Federal Motor Carrier, so where we are using this BSM, basic safety message, to minimize crashes between large vehicles and the passenger vehicles, commercial vehicles and passenger vehicles. So this is an ongoing project that we are using the same technology. So what we are finding that you see that this is our system, and this is the CV2X. It's same thing happened with pedestrian safety message and video safety message, same. So you see that our accuracy with this video system is much better. So you see we have the less error, right? So accuracy is very good. In terms of computational time, so you see that for our computation time for computing the alert, like whether they should get an alert, and this is the communication time, and this is the addition. The BSM end-to-end is computational time and communication time, but it is less than 100 milliseconds. So which is okay for a real-time application. If you're within 100 milliseconds, which could be okay. And we are trying to see that we can expedite the algorithm to make it much faster. But right now, this is the result we got from the field. So this is the intersection that we are live streaming. This is from Clemson. It's a Perimeter Road and Avenue of Champions, very close to our basketball stadium. So we are looking at the intersection, the pedestrian vehicles. And when our algorithm is detecting there is an imminent crash, we are informing the driver. So this is a real system. So this is the setup. This is the edge computing. So we have pedestrian roadside cameras and a pole. And we have also in the pole the Jetson NVIDIA device to process. These are very good for roadside computation, right? NVIDIA devices. So we are processing the data. And then we have so we are generating the safety alert, whether there will be an accident or not, based on the basic safety message and pedestrian safety message. And then we are using CV2X to send alert to your phone, to the vehicles, right? So you can take action. So, and we are showing the code running in the background. So in the TX2 to determine the accident risks. So we did not stop there, because we are saying that we'll send data from our video camera to a roadside device or to another computer, right? Video takes a lot of bandwidth, right? So we have to reduce it. So what we are doing, we created an algorithm, dynamic lossy compression. So you all know about lossy compression, right? So, but we did a dynamic lossy compression. So this is the setup. So the edge computing is sending the data that how much compression it should do based on the weather condition. So we have a weather monitoring based on, is it rainy, is it dark? It's like there are a lot of cloudy day. So all this environmental detection is done here, and it's sending the peak signal to noise ratio. So this is the peak signal to noise ratio, and based on that, and then it will determine that how much compress it should do based on the environmental condition, because we cannot compress it up below a certain threshold, because then the application will not work, right? So when you're adding too much noise, if the video is very hazy, then the application will not work. So we set up the limit, up to how much we can do this. So you see, this is for a pedestrian safety application, this is the real video, and this is a compressed video. But it's a dynamic lossy compression, so we compress just the right amount. And it runs, so you see that, so this is the pedestrian detection accuracy for different weather conditions. So this is sunny weather, light dark, medium dark, high dark, light rain, moderate rain, heavy rain. So we did a lot of analysis, and we found that we cannot have peak signal to noise ratio less than 40 decibel. So that's how we set up. That's our threshold, because we wanted to achieve 97% accuracy in pedestrian detection in order to be our system to be useful. So we set that up, And then, so 97% of was our threshold, and you can see the constant rate factor. So based on the PSNR, it selected the knob, selected that the CRF knob, that what CRF factor should be associated with the PSNR. And then, so all these, the signal to noise ratio and the CRF factor, we associated CRF factor. And then you can see that it, for heavy rain, so for light rain, it was perfectly fine. So for heavy rain, it was not going to like a 97%. If you look at the color coding, right? So, but still, it's not bad. Like it's over 90% accuracy, right? So, so we are compressing data a lot, and our video size is decreasing, but the accuracy is not decreasing that significantly. And if you want to read, this paper is actually in the Journal of Real-Time Image Processing. So we have done some work on 5G because we see that 5G is could be very useful for connected and autonomous vehicles. So we use a 5G millimeter wave. So it has higher frequency, but the range is a little bit less than lower frequency. So this is, we compared it for vehicle to infrastructure application. So we compared it with the IEEE 802.11p. So what is that? You're all communication experts. I was listening to your presentation. What is this? This standard? Anyone what this is relates to? Wave, right? The wave, the vehicular network standard. So we compared with the existing IEEE standard, 802.11p, and this is the 5G. So you see that it performs very well, right? The red dots outliers, and we have the plus and mean. So you can see for packet loss, it's pretty cool, right? Compared to the wave standard that is for vehicular networking, the industry standard, IEEE 802.11p. And then for throughput, we also find that 5G is much more advantageous. So this was our setup. So and then so you will need so for some areas you may not have 5G coverage with the 5G stations everywhere, millimeter wave base station, but in some critical locations, so for example in rural areas, you might deploy these type of stations. So that might be so this might be very applicable to our CR2C2 projects. Now this is now going to security. So it is the work I'm presenting actually are from our National Center on Cybersecurity and Resiliency. So why security is so important? So you know that in a cyber physical system, the communication is vertical, but IoT means that different cyber physical systems are communicating with each other. So there's a horizontal communication between the transportation CPSS, power grid, and anything you can think of, space CPSS, healthcare CPSS, right? So they're communicating with each other to serve rural areas, everyone, like city crowds, minority group, rural community, the recreational facilities, everyone is served equally. So all this is IoT, the horizontal communication. And my point here is, if you can disrupt service here, if you can attack the sensor node or any of the nodes, then that the fault that you interjected or the virus that you interjected here, it will propagate. So the entire city will be affected if you can attack any cyber physical social system. Either it's transportation, power. You see the attack propagation is very real. So through one, it will just horizontally propagate in an IoT environment, right? In a smart city, we are striving for the complete IoT, right? Internet of Things. So everything is connected. All the cyber physical systems is connected. So we have to protect each cyber physical system and also how they communicate with each other. So our national center is focused primarily on these 4 areas: security of resiliency of everything, transportation, infrastructures, and also another thrust area is user and data privacy. And also we're looking at society and environment. So what it means, security and resiliency, user and data privacy, how it will impact the society. And then this is one important area we are researching, You know, how much is like a quantum computer today? What do you think? They're going to buy a quantum computer for apartments, how much it would be? So 10 million, right? So if you want to buy this quantum computer, but the regular attacker will not be able to buy it, but a state can get a hold of it. They will have it and they can attack any system, and it's very easy to break the classical computers. For example, the encryption that is done in classical computing environment can be broken down by quantum computers very easily. So now we have then the quantum resistant encryption, right? So quantum offers a real threat, but also it offers a lot of opportunities, right? So, and it is in the development stage, as I showed, that it's very good for optimization. And also quantum AI is our favorite area. We are doing a lot of work, published a lot of work on quantum AI. So it offers a lot of opportunities. And we found that quantum computing, quantum AI works better than classical AI in many instances. So we are looking at the threats from quantum computers and opportunities from quantum computers. So so these are the 4 thrust areas of our national center. So now I was listening to a presentation, Masha, right, on the networking. So that's one of my favorite areas of research, wireless networking. So we started working on heterogeneous wireless networking. So what it means that no matter which network you are in, like Wi-Fi, LTE, DSRC, CV2X, they can seamlessly transfer. So a vehicle is moving from Wi-Fi region to DSRC or DSRC to LTE. So the transfer could be must be seamless. So we developed a lot of algorithms, and we tested in the field, and also we tested in a simulation environment with NS4, NS3, and now it's NS4, and with OpNet. So we did a lot of simulation testing. Also, we did the real world testing. So our test bed in Clemson is focused on heterogeneous wireless networking. It helps to ensure security too. When one network is attacked, you have to switch quickly to another network. This is like a very famous paper. It's like this paper. We did a real testing of heterogeneous wireless networking. Yeah, you can look at this paper. So my Dr. Day is now in Michigan State. Now he was my student when he did this. Now he's an associate professor at Michigan State. But so his area is HETNet. He works on HETNet. So you see that this is like a DSRC and LT. So it's switching between DSRC and LT based on where the station, base stations, which base stations are where. And this is for traffic applications. This is for data collection. So you don't care about delay that much, but safety, very, very important. You have to have the delay very less. So it will choose a communication technology that offers low delay, like CV2X or 5G or DSRC. So we have a trained model, AI-based model that knows where the base stations are and what they're offering and what are the functional requirements from the vehicle. So what type of functions, applications they are running. So one vehicle may be running some traffic data collection function, is providing data, but and it can also running the safety application, so collision avoidance. So we know that it's running 2 applications, so we'll connect that vehicle with the base stations accordingly. So, but that vehicle never loses the connection, because it will be very risky if the connection is broken. So this was done. So this is an example. We had DSRC. So the DSRC radio was here, right? And you see that when we were just using just DSRC, this is the coverage, not much, right? But when we're using LT and DSRC, the seamless switching, we had much larger coverage. And we have, are you aware of WiMAX? This is another wireless technology, WiMAX. So we found the same thing is happening with WiMAX, Wi-Fi, and the seamless data transfer. So, and you can see that the speed profile, so you can see that it's giving the speed like the speed kilometer per hour. So so that we are just detecting the speed at different points in our test bed in Clemson. So HETnet is good. Just one communication is not good. So that's the message. So, but HETnet, you have to design it in a way that the transfer is seamless in terms of vertical handover from one communication technology to other, and the horizontal handover. So it's from you are just transferring in the same communication technology from Wi-Fi to Wi-Fi, LT to LT. So our edge-centric handover system. So we have a deep learning model is selecting that this vehicle should go to another Wi-Fi base station or connected to another base station, or it should do a vertical handover. And so this is showing only horizontal handover, or it will go from Wi-Fi to LTE. So it is determining our deep learning model. So for horizontal handover, it's here. This vehicle is connected to the Wi-Fi base station 1. And after the handover, it decided that you should connect to the next Wi-Fi base station. Handover is here. So it's a horizontal handover. And our deep learning model is determining based on several factors. What are the requirements of the vehicle? What type of applications it is running? One vehicle can run multiple applications, as I said, traffic application or safety application. And also the base station, where the base stations are, and what are the power of those base stations. So now we compared with one of the most common handover techniques. So this is a vertical handover. So it is going from Wi-Fi to LTE, right? So from different communication technology. So we compared. So eco, that's so it's an edge-centric. It's based on our edge computing. So it's deciding which vehicle should connect to which. And then we compared with another system that are used now, decentralized handover. So the difference between this and this is, so here, this is, each vehicle communicates with the communication station, like base station, individual, right? But in ours, we actually communicate through our edge. We communicate with the vehicle where they should go, which base station they will be connected to. So this is here. Each vehicle communicating. We are here. We are telling vehicles where they should communicate to. We know vehicle is sending data to us. They're connected vehicles, but we are deciding our edge device that where they should communicate to. You can see that with this. This is a decentralized system. The delay in terms of packet loss, you see that our system packet loss is less. The eco is our system, the AI-based system, where our edge device is deciding where the vehicle should communicate to, and the DHO is where each vehicle is communicating with the base station. So our system was found to be much better in terms of packet loss and number of handovers too. So this is one thing we software-defined networking. We presented this in the Las Vegas Consumers Electronics Show, and it was very popular. The system. So what we showed to the audience in Las Vegas that so we have a system. So this NVIDIA Jetson TX2. So we had a AI-based cyber attack detection too. So we are detecting intrusion detection. So there was an attack on this network. Wi-Fi network. If someone attacker attacked our Wi-Fi access point, and it then just propagated to the vehicle. So what we did then, we had an SDN controller. We said, and we showed in real with the SDN controller that okay, so just initiate a handover. So what the SDN controller does, it just tells the SDN switch that now you should change it to Wi-Fi's attacks or go to connect to LT base station, right? So it does, so with the AI running here and this SDN controller, it is done very, very quickly. So this looks simple, right? But the way it is done, it is very, very quick, the way the handover happens, right? So that's why I think the Las Vegas audience were impressed because how quickly this is happening, attack detection to the switching of the network. So yeah, again, my students are awesome. So they did this first in the lab, and then they were invited to present in Las Vegas. So yes, it was done very, very quickly. So quantum AI for resiliency. So we saw that if we train the perception module in autonomous vehicles through quantum AI rather than just classical AI or any AI model, it is much more resilient against cyber attacks. So we tested in the field. So we ran in the whole city of Clemson, and we were seeing that how we can attack the perception module. One with when perception module we are trained with the classical AI, and another with quantum AI. We'll see that when the attack happened, like there are a lot of attack models we can attack the AI model by, and with the adversarial attack is happening, then our quantum AI is very resilient. So this is, we call it hybrid because the data is in bits and we convert into qubits. So we call it hybrid, but just classical algorithm, it is not resilient enough, but you will it's very difficult to break the quantum AI model. In case you're wondering, that's me. I'm not wearing sunglasses, so you might not recognize me. So and we have published many papers on this area. It is. Oh. So this is another paper you can look at, but we have a lot of IEEE sensors. So we have papers on the same classical AI and quantum AI. You can see that these are different types of attacks, adversarial attacks, projected gradient descent attack, gradient attack, first gradient attack. So the orange is our quantum AI model. It is performing better in terms of accuracy. So all the AI measures, recall, so it was doing much better job in protecting the perception module. So if you're making an attack, and then if you have quantum AI, so it will be much more resilient. So, and we have seen that in many instances and in all our research. How we are doing on time? So
we have 5 more minutes.
Oh, so my favorite topic is still there. So we are doing something very unique in hardware security. You will not see many universities have a lot of resources or research on hardware security, but we have some amazing students. I'll just shout out for Pushpo. So she is a PhD student. She is leading a lot of our hardware security work. So and several other John. So we are doing a lot of work on the hardware security. So, I will show there are a lot of hardware security attacks. It could be side channel, right? Where the data is leaked and the adversary is getting the data. But today, we'll talk with the stealthy attack, Trojan, right? Trojan virus, so the Trojan horse. So what they can, someone can interject a circuit, adversarial circuit in anything you buy in your computer, in your cell phone, in a traffic controller, right? So this is an integrated circuit, right? It's everywhere. It's in your cell phone. It's everywhere. So in a traffic controller. So, and it's manufactured. You don't know where it's manufactured. If you know too, an adversary can interject an adversarial circuit, Trojan circuit. And when you test for functionality, for functions, when you test for functions, it will work okay, right? If the phone is working the way you intended, the traffic signal is working the way you intended. But it can be activated for different ways, and I will show that. And then it will mess up everything. It can have a serious consequence if the Trojan is activated. So yes, you see in our transportation, we have in cars, buses, in traffic signal controllers, in a roadside device, signal here. So we have these circuits. Now we can trigger the Trojan virus. We can trigger with something, and we'll show that with a trigger. And we can trigger it after 1 month you purchase the device. So we can set it up when an adversary will trigger it. And then the payload output will be, we can mess up your, whatever you're trying to do. A traffic signal controller can see green in all direction in a busy Atlanta area. They will see green in all direction because the Trojan was activated. So where the Trojan can be interjected or added, a vendor, intellectual property vendor can interject a Trojan. So it could be someone you are buying a component for your signal from a intellectual property vendor, and they can add a Trojan's adversarial circuit, right, to that component. And in the design, designer could be an adversary, they can add that. And also in the manufacturing process, in the foundry, they can add the physical in this. When they're manufacturing this IC, they can add that circuit. And then when you test it, everything is fine, right? Everything is fine. But when you deploy it, things will go bad. So how they can activate an adversary? Time-based, you can say that after 1 month, Dr. Ali buys like a sport, or you buy your new autonomous car. It can be activated after 1 year. It will be to the wish of the attacker. It can be activated by temperature, right? And it could be a digital input. Any input can activate the Trojan virus, right? And it's stealthy. That means that you will not know it's there. So it's very hard to detect Trojan, right? So we like to do difficult things. So we say, let's detect Trojan. So what will happen? Your data theft, they can steal your information, system will malfunction. They can steal your secret, unauthorized access, right? Data tampering, your system will be damaged, and operation will be disruption, right? So it can do a major damage to any hardware system or any digital system. So this is the experiment we did. So for toll collection system, we showed in a simple, this is the digital IC, integrated circuit, that for regular toll collection, so for heavy duty, say it's 13 cents, just for example. But we inserted a Trojan virus, okay, it's adversarial circuit, and we activated as a time-based activation, and then it was showing this $2. It could be $200. I'm just being nice, so I just kept it to $2. But you can think that if we can do this for toll collection, we can do for everything, right? I'm just showing, we did in the lab that how easy it is to interject a Trojan and activate it. But this is the important thing. Effect of Trojan insertion on chip power. What do you see in these two graphs? There's not much difference, right, in the power. So this is the dynamic power when the system is in operation, and the static power, like when your electrical system is consuming power. This is the total power. But the dynamic power is not much different, 0.032, 0.031, right? So, but if you test it, let me see if the power consumption is more, because you have an additional circuit, right? It should be more, but it's not. That's why we call it stealthy attack. So in a stealth mode, so it can be done in a stealth mode. So it's very troublesome, because we are buying like a lot of foreign cars and devices and so on. So the insertion would be much easier to do. So we are doing research with FPGA board integrated circuits, right? My students, I forgot to mention another student working on hardware security, Abiyad. So he will be saying, why didn't you say my name? So Abiyad, so you're also working on it. So I have to give credit to all my students who are working on it. So and now this is a Cadence, an electronic design automation platform. You use it here. So yeah, so we used it for our, so we can do it in the real device, but we can use the Cadence, right? So this is like, if you have an abstract design, right? So we can do it in RTL, register transfer level. So it will have the wire and the gate. So you can actually design the real circuit, okay, using this tool. Genus, what is this? Exilium. It is a simulator, okay. In Cadence, a simulator. So it simulates the design that you created, right? So it simulates the design. So you can see what's going on, input, output. And Jules is so there are other models too, Cadence. So we are using Cadence from the Clemson as a license. And so we are using Cadence. And Jules is around dynamic power analysis. So it does that. So we are looking at the power consumption. If there's an additional Trojan circuit, I will go fast now. I worked as an auctioneer, so I can talk fast. So you see that after Trojan disabled in the IC, Trojan triggered. So we did not, Trojan was, so in the red, you see we triggered the Trojan and the first one, the green, it was not activated. But you see the difference is minor, right? Between two and what in the circuit, so you understand that in what we did, the plain text, we have an encryption circuit. So we wanted to encrypt data through that circuit. So AES encryption and then the ciphertext. So this has happened from this input, this output in our circuit. And then we saw this is different, but it is with the AI deep learning, we're using deep learning to see that when the Trojan is triggered. So we can use deep learning. We are finding that you use deep learning so you can find out whether there's a Trojan or not. So which will be a very big contribution to our infrastructure systems. So now our research project, so this is very unique. I want to say that we are developing a national platform. So anyone with a port or highway system can take our platform and implement. They should be protected. That's our goal. So we call this application our foundational project. And that tool can be used for assess the risk, and it will provide solution in terms of software and hardware. And also we are providing continuous updates. So all our partners are working on developing this platform. And so what will be the result? Secure application. And also we are working with the legal experts, right? Policymakers on the policy and guidelines. And we also big on cybersecurity testing. I'll finish in, okay. So, and also when we are developing the platform, we are getting a very detailed level. We are looking at what's going on in the industry, right? So application decomposition tools, so WASP, KRIS, threat modeling tools. So we are first using all the threat modeling tools and also threat identification ranking tools from MITRE, from ATA, from Stride, Fast Octave. So we are working on that. And also we are looking at standards, as I've shown before, mitigation and response. So the MITRE's common weakness system. OWASP is a very good security verification standard. So we are looking at all these tools available to us, and we are seeing that what we can do more to make sure the system is fully protected. Our transmission system is fully protected. And so we are running different applications. So this is showing one application so that we started with securing with existing tools and the tools that we are developing. So this is from the National ITS architecture. It says it's suggesting what should be encrypted, not encrypted. So we are following their guidelines, but we are developing our own tools. And so this is how we are developing this application. So these are so we talked about the foundational projects. These are the projects we are funding, the mini projects that will provide some input to our the foundational projects. Now, so we are using the GNSS navigation security. So it is looking at how you can protect the satellite signal. So no one can spoof the signal. So you could be in real trouble if your GPS signals are spoofed, right? And we also equity and social agency. We'll work on policy with the legal experts. So we have a variety of projects, and we're working on hardware security. So a lot of different projects, but it's different universities are working on these different projects, but together we are working on the platform. So I'm a big proponent of security testing. So this is very important. So we are developing a test bed that can test all the cybersecurity. So right now you have cars, you test it for crash tests, right? Crash tests, but there is nothing now that can test the security of your car or security of a traffic signal controller. So we are in the process of developing a framework and how to test it. So we are developing security test bed. So we are doing first in Clemson, but also we are working with different universities our partners to develop a similar test bed. So it can be real test, it can be a software in the loop test. So yeah, so it could be a simulation test, it should be an integration and the real test. So, and with combine, you will see that is my circuit cyber secure, then you give a certificate, right? So then you can have system implemented. So that is the So we have this famous quantum AI lab that we created. So it is used for security detection, mitigation, resiliency. We have these 3 projects going on in quantum. So we're using quantum for LSTM for autonomous track platooning. The project is completed. And for quantum CNN, we are going to the theoretical level that why quantum CNN is working better. So we are trying to prove the theoretical reason behind it. So this is a very theoretical project. So it will help us to understand the real power of quantum. We are going to the quantum physics to do that. And also we have a post-quantum cryptography for blockchain-based VANET. So it will be much secure than whatever communication we have today for VANET. And we offered courses at Clemson and Benedict College. And we offered a lot of workshops on quantum computing through our centers. So this is the next frontiers. As I was mentioning, leading to this, the GNSS security, the satellite security. So these are very, very important now. So space will be a multimodal system, right? It's another, we see that so many companies are investing on space travel, right? So it will be a part of our transportation system. But you see that this is like where we have a lot of vulnerabilities. And the space CPS, CPS. So you see that some space shuttles by some companies, it's a fully automated system. It automatically goes to the space and comes back. There is a ground control, and the communication is wireless communication, which is CPS, right? Your sensing, communication, and compute. So these are the components, the ground system, computer system. This is in your spacecraft, and this is in your satellite, right? So this all can be attacked, and the attack can be propagated. So you see that, so attacker can attack your satellite. You can from space and adversarial, but you can also attack from the ground. And there is a ground control, right? The control center. Some attacker can attack that, and it can propagate to the space. So it could be very dangerous. So, and if you can attack the space, it could be compromise every CPSS we have, every cyber physical social systems we have in the art. So it could be a real scary. So we have to focus on that. So the thing we learned through our transportation system, autonomous vehicles, traffic signal, this is CPS. So we can actually apply it to space too. So whatever you're learning, either you're in civil engineering, electrical, it has an application beyond what you're just doing, right? Lot of NASA technology we are now using in our household. So I see the same way. What we are doing, it's not only bounded by transportation. That's what I tell my students. So these are my superstar students. So these are my current students. So Megha, she's our coordinator, but she's also an engineer. So she has a master's in engineering. And this is, I call him Dr. Quantum. So he worked on Oak Ridge National Lab many years in quantum computing. So he's our postdoc. And this is our Dr. Sabir Salek. He's our senior engineer. So these are our staff. So what happened? Huh? Why look more handsome? This will, I think, unauthorized access, tampered image. But it's good. I will keep it because I look better. Yeah. He's my best friend, Evangelist Kaiser, right? Friday. Oh, I don't like him. So, but the other one was better. So you can look at our work in this, and then, so this is our vision. So safeguard the transportation and infrastructure. So,
Thank you so much.
thank you.
Thank you so much. Great talk. Let's start with the cyber slide. If there is a question there, and then come back to the conference room here. So, is there any question on the cyber side?
Call it cyber. This is a physical side.
Yes.
No, there are no questions at this time. Please remember to use the mic when anybody in the room is asking a question.
Thank you for the great presentation. It was very entertaining, teaching. So, my question is about the quantum part. When you mentioned quantum optimization of quantum AI, is it
inspired by quantum mechanics, or you are literally doing quantum computers?
Awesome question. So, yeah, awesome audience. So it is, all the quantum computers work based on the quantum mechanics and quantum physics, right? So the superposition and entanglement, two qualities of major criteria for quantum. I think those works in quantum computing. So those quantum physics are interpreted in the computing side of it. So we are not working on the material side or on the physics side, although we have some physics because we are using the quantum computer. So, but you have to understand some of the terms for what does entangle means, why there is a crosstalk between the qubits. So you need to understand some basics of quantum physics, but then you are just focusing on the computing side. So we are using different quantum machines, right? So D-Wave runs on one technology, so IBM runs on different, for different systems are better for different things. Right now, you can use quantum computers through web services.
So you are using the web service part. You don't have.
No, I don't, we are not that rich yet. So yeah, we are using the web
I
services.
saw the picture that maybe.
No, not yet. So, but yes, Ali will get and will work here. So, but yeah, yes, so much resources here. But yeah, we are thinking about getting smaller quantum computers with less money, but we are working on that. But right now, but we are using different services, D-Wave, IBM, Amazon, brackets, right? So all those quantum computers. But we have to pay for the services. So the other.
Yeah, so in one of the earlier slides, you mentioned that you tested out the virtual traffic light for CADs and the performance was really good.
Yeah.
So I'd like to know, was it done in the presence of conventional vehicles? If yes, how was the cooperation between the conventional vehicles and the CADs at intersections for the virtual traffic lights?
So, so there is like a software called ATMS now. So you can, so that enables the coordination between signal and vehicle. So if you have a controller can send you SPAT information, signal phasing and timing. So we can get the real phasing and timing information from the traffic controller. And the vehicle can also send data to the traffic controller. And vehicle through LT can connect with the Amazon server. So just with the LT connect, it was connect with the server.
Yeah, so in a situation where this is a case where the conventional vehicles are able to communicate to the CADs, right? So how then, let's say at the point in time where conventional vehicles are giving the green light to go, is it the same time the CADs are also giving the green light to go?
So awesome question. So you have some super students. So yeah, so you're just like me, so very lucky. So the thing is, so here what we are showing that all vehicles are connected. So they have a radio. You can buy a radio $500, right? But we did another project, but not here. It's all connected, right? So it's easy to form the platform. But we did another research where we ran adaptive signal control with a mixed vehicle. And we found that, so there's a different algorithm, but we found that if you have only a few vehicles connected, we can achieve the same goal. So what you have to do that you have to find two connected vehicles CAD that will be the leader of the plot loop and the back of the plot loop. So if you can form that, so you have to find out in a mixed traffic who are connected. So and then you can do that. But that's another paper I can share with you. But it was a mixed traffic. But what I showed here, it's all connected.
Switching back to the cyber side, is there any question on the cyber side?
Nope, so far no raised hands or comments in the chat. Only Dr. McBride apologized for not being able to make it in person.
Yeah, Miss so Dr. McBride. So yeah, we're looking forward to meeting you, but yeah, we'll meet in the conference.
I just have a very short question, but like excellent idea and presentation. I'm curious from like a whole citywide point of perspective, what is the geospatial scope of such attacks? Like usually the examples you showed were in section based or maybe a total connection based, but I'm curious like to what extent in that geospatial.
So I like movies, so I can give a movie. How many of you watched the Netflix Leave the World Behind? So they leave the world behind. So the whole New York City is attacked, but through just satellite, right? So one component. But what I said that the IoT, so your attack can propagate. So if you can attack one system and if they're connected. So now everything is connected and open, right? So, yeah, so if you buy any car like a 2023, 2022, you will get scared how connected each vehicle is, right? And through the vehicle, you can propagate an attack to an electricity grid. It's an electric vehicle. You can propagate an attack to your home, smart home. So now we are talking about smart cities, right? So everything is open because you are opening the wireless communication, your phone. So through your phone, you can propagate an attack to your car. So, and from car to electricity grid to your home. So it can propagate. So that's why I like this IoT diagram that you can actually horizontally attack the whole city can be degraded.
What is like the timeline of such, like how quickly does that attack happen? Is it minutes?
It can be in some situation, if the satellites are attacked, so all the transmission system will fall apart, right? So it can be very quick depending on the how good the attack is. So it can happen quickly. So yeah, so I read some books that right now we so for the I actually there was an interview IEEE asked me that whether there is any protection against cybersecurity, but we did not focus on cybersecurity a lot for any transmission system. But so it can happen very quickly if the attacker is very sophisticated. And with quantum computers, you can create such attacks that you may not have any defense. So like encryption algorithm, right? So the RSA, so that can be it's very hard if you have done corrected encryption, but your quantum computer can break the encryption very easily. And you can see that a hardware attack, right? So we are not focusing on hardware security a lot. So any of these devices we are buying from anywhere, right? So they can insert anything and you will not be able to find it through testing. It works as it should work, right? But they can activate it through like a lot of different things we saw. So it can, if the attacker is sophisticated, it can be very quick and devastating.
Any other question?
So you presented like one slide in which you were talking about Trojan app, and in that you show like you're using AES encryption algorithm to convert plain text to cyberattacks. So I was curious that if you're testing like through other encryption algorithms as well, like
Yeah, we are testing for different things. Yeah. I'm just showing an example here.
okay. And there are like different attacks, like apart from Trojan as well, so like backdoor attacks like that. So are you working on that as well?
We have a big, I just named the security, my students, superstar students, but we have professors too that are working on experts on backdoor attack and experts on that side channel attacks. So we have a team that are working on the hardware security, and we have a couple of labs at Clemson University on hardware security. Senkai, so he's very famous and side channel attacks. But he's working with me on some of the projects.
Hi, Professor. Thank you for your presentation. One of your results you showed the performance of 5G versus the current environment. In
Today, setting
and 5G is much better. Yeah. What's the status here? Can we consider from these results that the current standard is obsolete and we have to move to 5G? Or
yeah, I think 5G will definitely advantageous because we know the throughput is higher and it will be more compared to 4G is more secure. It's not 100% secure, but it's much more secure. But the thing is that you have to have those 5G stations, right? If you want to implement in Greensboro, so you have to have those base stations. So there's a cost associated with it. So then definitely I'll go for it.
Any question on the cyber side? Any question here?
Nope, no questions so far.
Physical side one. One question.
So I do have one question here. So the hybrid network, communication network that you had, did you made any analysis or can you comment on the impact of the handover when you're switching from one network to another network, let's say on packet dropout and all of those sorts of things that could happen, how we can mitigate that impact of the handover.
So there was, it's much better than the, I showed you decentralized. So only one issue is this is like one edge device is doing the handover, right? So it's more of a centralized system. But the others you saw that vehicle is sending what we use today. So there could be a single point failure. So if that one does not work, so that could be one of the limitation, but you can have a redundant system. So, but in terms of a handover latency, the packet drops, it perform better than what we have today. The only thing I worry about is it's a just centralized system, so there could be a single point failure.
Last question.
How can you be like evangelist?
And it was one item about optimizing computation and computation. So is that possible for like managing computation workloads with the onboard computation that they have outputs?
Yeah. So that's also a very good question. So if you have to like for if you're a quantum computer, you cannot put a quantum computer in the car, right? So there is a latency that you send the data and getting it back. So if you use a commercial quantum computer, so your work may be in queue, right? So but for safety application, you cannot have that in queue. So you have to have a dedicated space. But yeah, so someday if you have a real-time safety application, I'll say that that could create a problem because of the delay in uploading and downloading time. But we found, yeah, so that could be a problem, but unless you have a dedicated space in the commercial clouds, or the quantum becomes, so like there are some efforts going on to make it smaller, and so it can, right now you have to put the computers at certain very low temperature, right? So when those computers can be placed anywhere, so I think that would be more advantageous. But some application which is not, you don't need a real-time feedback, I think.
Great. So it's already 1:10, and thank you everybody for joining this presentation, both on the hardware side, those who have been here in person. Thank you so much also, Professor Ronnie Chowdhury, and it was really inspiring. And I'm sure that there will be some follow-up conversations, so feel free to reach out to
One comment I will make. So I tell my students, don't just focus on what you're working on. It has a much broader application. So when I see a shuttle, autonomous shuttles, everything that we are doing now can be applicable there. So just think beyond what you're doing.
Great. Thank you. Thank you for this last comment. Thank you so much. Thank you, everybody on the side.
Thank you.
Thank you.